Hi, I'm Niranjan Bhujel. This is ECE 591 literature review of the paper titled Smooth Exploration for Robotic Reinforcement Learning. And this is the outline of my presentation. First, I will briefly talk about reinforcement learning and then exploration in reinforcement learning and different methods of exploration, motivation for using generalized state dependent exploration, the performance of GSDE compared to other strategy, and conclusions and reference. So the reinforcement learning is the training of model to make sequence of decision. For example, consider a scenario of a video game. We have to make a decision at every time which button to press. Similarly, in the stock market, we have to make a decision how much stock to buy or sell or hold based on given information. Similarly, in the room cleaning robot, it has to make a decision which direction to move based on the information available from the sensor. So in all these scenario, few things are common. Some information are known, and the objective is to maximize or minimize some number, like score or the profit. So the model needs to learn how to make best decision based on the no information. Here I will talk about some basic term used in reinforcement learning. The environment is where the decision is applied. The state is known variable of the environment. This gives the configuration of the environment. Reward is a performance score that says how well the agent is doing. Action is the decision made by the agent, and the agent is just a machine learning model. And policy is just a mathematical function that maps state to the action. And the episode basically means the start to the some terminal condition. This terminal condition could be like the end of certain level in a video game. Like in some task, there is no default terminal condition. So in that case, the terminal condition has to be defined to make it episode. Reinforcement learning involves training through multiple episodes. Now the question is, how does agent learn to figure out best decision? By exploring the environment. So by exploring, it means trying the random action and then observe the reward and then improve the policy. And then again try the random action and improve the policy and so on. So this is how the agent learns. Now, since the policy is a mathematical function which needs to be learned, we can represent that function with a neural network. The input to the neural network is the state, which could be like the image or time series data or just a number, and the input layer should be chosen accordingly. And the output is the action. And the action here represented by A can be written as the function mu of the state and the parameter theta mu. This theta mu is the learnable parameter of this neural network. So this policy, it is deterministic. For example, let's say I encountered the same value of the yes state two times. Then both of the times the same action would be taken because there is no randomness in this policy. So if it takes the same action for a given scenario all the time, then it would not explore the better action, and hence the policy would hardly improve. So it must explore, and then uh, we have to add the exploration noise so that this part gives the deterministic action, and we add some random noise so that it starts exploring the environment. This epsilon is very important. It plays very important role in success of RL algorithm for a particular task. And further, there are some effect of bad exploration. The trajectory could be noisy. It might causes increased wear and tear of the motor or other equipments. And sometimes if the exploration is very poor, the policy would not improve. So since the exploration is very important, a lot of research has been focused on different exploration strategy. The first one is very simple. The epsilon is sampled at each time steps from Gaussian distribution of mean zero and standard deviation sigma. This sigma could depend upon the state or it could be independent. This epsilon is sampled at each time steps. So the main drawbacks of this approach is inconsistent exploration. Most of the system, they acts as a low pass filter, which means it does not respond to a very fast changing input. For example, if my input is changing very fast, the system would only respond to the average value of that input. Since the epsilon is sampled at its time step, the action, it acts as a high frequency noisy input to the system, and the system does not respond to it, and the exploration would not be sufficient. Another approach is parametric noise. So instead of adding the noise to the output, we add the noise to the value of the parameters and use this parameter of a neural network to select the action. This epsilon is sampled at the start of each episode, which means the same noise is used throughout the episode. So the main drawback of this approach is the size of the epsilon is same as that of theta mu. So if my neural network is very large, it has millions of learnable parameter, then the size of the epsilon would be very large. So it limits its application to the larger neural network. Further, since this same value of epsilon is used for the entire episode, it is very difficult to improve the policy when the episodic length is very large. So the another strategy is the state dependent exploration. In this strategy, the epsilon is the linear function of state through some parameter theta epsilon. This theta epsilon is randomly sampled at the start of each episode. This theta epsilon is different than the theta mu, which means even if the neural network is very large, we can still choose the theta epsilon to be smaller. And so this solves one of the problem of the previous strategy. However, the limited exploration for long episodic task is still there, and our assumption of linear dependency on the state, it might not be the like the best assumption. So keeping all those drawbacks in mind, the paper proposes generalized state dependent exploration, GSDE. So instead of sampling theta epsilon every episode, it is sampled every n time steps. This n is defined by us. So we have the option on how frequently we have to sample. So this solves one of the problem, like limited exploration for long episodic tasks. We can just sample more frequently than the case with the entire same sample for the entire episode. So and another problem, it solves the problem of linear dependency by introducing some nonlinear function z mu of s. So this z mu of s is nonlinear function, so which should be learned from this neural network. So to learn this z mu s, the neural network outputs another it provides another output z mu s. So since this z mu s is learned from the data, this the performance of this would be better than the linear assumption. And here the exploration strategy is partly learned from the data itself. So this paper uses these 4 environment to make a comparison. So the first one is half theta, which is shown in the figure above, the first one. So it is just like the robot, 2-legged robot, and the objective is to make it learn how to walk. And the second image, it shows the walker 2D. So hopper. So in this case, the objective is to learn to move by jumping. So there are other 2 environment which I have not shown in the figure, but it is available as pibulate or gym environment. Uh, it can be easily found online. So if you're interested, you can look into it. Um, okay. And the paper also introduces continuity cost. This continuity cost is basically the difference between action at two consecutive time steps divided by max squared and take the average value. So this continuity cost basically represents how fast my action is changing. If my action is changing very fast, then the difference of these two would be large, and hence the continuity cost would be large. If my action is changing very slowly, then this would be smaller. So which means this continuity cost can be used as a proxy for wear and tear. For example, if the action is moving very fast, there would be higher wear and tear, and at the same time, this continuity cost would also increase. So we can use this continuity cost as an indicator for wear and tear. So in the this graph shows the normalized return and the normalized continuity cost for using different exploration strategy. So the normalized return is like a performance score. So higher the normalized return, better the algorithm is um, working. So and the normalized continuity cost, we want this to be as small as possible. So the ideal area would be this. However, there is always some trade-off, so we cannot always get to this area. So if we look at unstructured exploration strategy, the continuity cost is very high, and it is also giving pretty good return. And if we see the parameter noise, continuity cost is highly reduced, but at the same time, normalized return is also reduced. So what GSDE does is GSDE, it gives us the option to fill the area on this gap so that we can choose based on our requirement. So maybe we can just reduce the value of the n sample interval and get the higher reward, and but at the same time the continuity cost also increases. Or we might increase the sample interval and move to this area. So we have the flexibility. And another thing is, so this GSD episodic. In this case, the value of n is set same as the episodic length, and the parameter noise. In the case of parameter noise exploration as well, the noise is sampled at the start of each episode, and the same value is used. So in that sense, these two are similar. However, the GSDE performs better than the parameter noise, and uh, the value of the continuity cost is almost similar, but the normalized return has a large is very is large in the GSTE case. This is um, probably because in GSTE the strategy is the exploration strategy is partly learned from the data. So and in this case, uh, GSDE is compared to the state dependent exploration SDE. In this case, the same four environment is considered, and two algorithm is considered, PPO and SAC. The PPO stands for proximal policy optimization, and SAC stands for soft actor critic. These are the like reinforcement learning algorithm out of many other types. So and the original and the latent one. So the original one is the SDE, and the latent one is it refers to the GSTE. So in this case, in some cases we do not see any significant difference between them. However, in some cases, the difference is very large. For example, in the case of Walker 2D and the Hopper using PPO, the difference is very large. And the graph on the right, it shows the influence of sampling interval on the Walker 2D environment. So when the value of n is set same as the episodic length, the score is lower. As we increase the sampling interval, the return increases, and after and if we reduce it further, mm, the value of the score is reduced. It is because when the sample is done very fast, the exploration become inconsistent. So in the conclusion, we can say that GSD has flexibility to get a good balance between the return and the continuity cost. And the exploration strategy is partly learned from the data, making the GST better than the parameter noise. And these are some of the references. So the first one is the paper itself. The second one is the gym library from OpenAI. The third one is the GitHub link to stable baseline 3. This is the reinforcement learning library based on PyTorch. And the remaining two are just the YouTube video that shows how those half cheetah and walker 2D what they are. Thank you.